Definition and significance of four-quadrant projection in engineering graphics. In engineering, drawing a three-dimensional object is shown on a flat sheet by projecting its features onto several orthogonal planes. The four-quadrant system divides the drawing area into four sections, quadrants like a Cartesian graph. Each quadrant holds one view of the object, usually the front top right side, and sometimes the auxiliary view. Clarity by separating views. Engineers can read lengths, angles, and relationships without the lines overlapping. Standardization. Most manufacturing shops and CAD packages expect the same quadrant layout, which speeds up communication. Real-world analogy. Think of a smartphone with four apps arranged in a 2x2 grid. Each app is independent, but together they give a complete picture of the phone's functionality. Similarly, each quadrant gives a piece of the object's geometry. The four-quadrant approach is the backbone of first angle, used mainly in Europe, Asia, and third angle, used mainly in the United States projection systems. Both systems use the same three principal planes: front, top, right, but they differ in where the projected images are placed relative to the object's imaginary placement. First angle, the object is imagined in the third quadrant. The view is projected through the object onto the opposite side of the plane. Quadrant layout typical for first angle: Quadrant 1, top view; Quadrant 2, front view; Quadrant 3, right side view; Quadrant 4, auxiliary if any. Third angle, the object is imagined in the first quadrant. The view is projected away from the object onto the same side of the plane. Quadrant layout typical for third angle: Quadrant 1, front view; Quadrant 2, top view; Quadrant 3, right side view; Quadrant 4, auxiliary. Analogy: imagine shining a flashlight on a sculpture. In the first angle method, the light passes through the sculpture and the shadow falls on the opposite wall, so the shadow appears on the far side. In third angle, the light shines away from the sculpture and the shadow lands on the nearest wall. The wall chosen for the shadow is what determines the quadrant placement. Mnemonic: first angle, project through opposite side; third angle, project away same side. Set up the reference axes. Draw a lightweight coordinate system: X horizontal, Y vertical, Z out of the page. Mark the origin O where the three planes meet. Locate the 3D point P, X, Y, Z for a manual draft. You can use a ruler and a set square. From O, move X units along the X-axis, then Y units up the Y-axis, finally Z units along the Z-axis using a depth gauge or a perpendicular line. Mark P. Project onto the front XY plane. Drop a perpendicular line from P straight down to the XY plane parallel to the Z-axis. The foot of this line is P sub F, X, Y, 0. Plot P sub F in the quadrant that holds the front view. See the layout table above. Project onto the top XZ plane. Drop a line from P parallel to the Y-axis to meet the XZ plane. The foot is P sub T, X, 0, Z. Plot P sub T in the top view quadrant. Project onto the right YZ plane. Drop a line from P parallel to the X-axis to meet the YZ plane. The foot is P sub R, 0, Y, Z. Plot P sub R in the right side quadrant. Check quadrant consistency. In first angle, the top view goes opposite the front view, so the top point is placed on the opposite side of the front point. In third angle, both go to the same side. Practical tip: use a drafting triangle, 45 degrees, 45 degrees, 90 degrees, to keep the projection lines perfectly orthogonal. A CAD program automates this with invisible construction planes. Example: suppose P equals 30 mm, 20 mm, 15 mm. Front projection: 30 mm, 20 mm placed in Quadrant 2 first angle or Quadrant 1 third angle. Top projection: 30 mm, 15 mm placed opposite the front view in first angle, same side in third angle. Right projection: 20 mm, 15 mm placed in Quadrant 3 for both systems. Right side view is usually unchanged. Coordinate transformation equations for converting 3D point coordinates to their projected 2D representations in all quadrants. The mathematics behind the projection is simply the removal or dropping of one coordinate component. The transformation depends only on the chosen view and the projection system. Let P equals XYZ be the 3D coordinates. The 2D projected coordinates in each view are: front XY view P sub F equals XY, top XZ view P sub T equals XZ, right YZ view P sub R equals YZ. To map these 2D points onto the drawing quadrants, we apply a quadrant sign matrix. The draw x and draw y vector equals the matrix with sxq in the top left and syq in the bottom right multiplied by the vector x proj y proj. Where, for first angle, the top view uses sxii equals -1 mirrored horizontally and syii equals 1. For third angle, the top view uses sxii equals 1 and syii equals 1. The front and right views usually keep the sign positive in both systems. In compact form, draw x comma draw y equals sigma x times x proj comma sigma y times y proj. Sigma x and sigma y belong to +1 or -1, depending on the quadrant and projection method. Example for first angle top view. Draw x comma draw y equals -x comma z. If x equals 30 millimeters, z equals 15 millimeters, the drawn point is -30 millimeters, 15 millimeters placed left of the origin in quadrant 2. These simple linear transformations are what CAD kernels execute when you switch between first angle and third angle display modes. Common projection errors and tolerance checks specific to quadrant projections. Quadrant swap, front view appears where the top view should be or vice versa. Detect by comparing the label F, T, R on each quadrant and verify against the chosen projection system. Remedy, reassign the views to the correct quadrants and double-check the first versus third angle flag. Axis mirroring mistake, a dimension measured on the drawing is opposite in sign negative to the real part. Detect by using a coordinate check. Pick a known point, for example 0, 0, 0 or x 0, 0 and see where it lands. Remedy, apply the correct sign factor, see transformation equations. Scale inconsistency, one view is drawn larger or smaller than the others. Detect by measuring a common dimension, for example the length of a shaft on two views, they should be identical. Remedy, ensure all views use the same drawing scale 1:1, 1:2 and so on. Projection line misalignment, projection lines are not perpendicular to the plane, points appear offset. Detect by extending a projection line and seeing if it meets the target plane at a right angle, use a set square. Remedy, redraw the projection lines using orthogonal construction tools or snap-to-grid functions. Tolerance overrun, the projected coordinates deviate beyond acceptable tolerance, for example greater than 0.1 millimeters for fine parts. Detect by performing a tolerance check. Calculate the difference between the measured drawn coordinate and the theoretical coordinate using the transformation formulas. Remedy, adjust drafting technique, use finer drafting tools or refine CAD grid resolution. Real-world analogy, think of a GPS map that accidentally flips the north-south axis, you would end up driving the wrong way. Similarly, a quadrant swap can send manufacturing down the wrong path. Tolerance checklist for quadrant projections. Number 1, verify drawing scale. Number 2, confirm projection system, first versus third. Number 3, check axis direction flags plus or minus for each view. Number 4, measure at least 3 reference points across different quadrants. Number 5, ensure all measured deviations are within the specified tolerance, typically plus or minus 0.05 millimeters for mechanical parts. Auxiliary views are extra projections taken on planes that are not the principal ones, usually to show inclined or hidden features clearly. In the 4-quadrant layout, the auxiliary view is placed in quadrant 4 or sometimes quadrant 2 for first angle. Here, how to handle it. Identify the feature, for example, a hole drilled at a 30-degree angle to the front plane. Choose the auxiliary plane, a plane that is perpendicular to the feature's axis. For a 30-degree hole, the auxiliary plane is inclined 30 degrees from the front plane. Project the feature onto the auxiliary plane, use true length projection. The line is drawn at its actual length, not foreshortened. Place the auxiliary view in the designated quadrant. Mark it clearly with a label AUX. Step-by-step drawing example, first angle. Draw the 3 principal views in quadrants 1 through 3. In quadrant 4, draw a faint reference rectangle representing the auxiliary plane. From the front view, draw projection lines at 30 degrees to the horizontal. These intersect the auxiliary plane rectangle at points corresponding to the hole edges. Connect those points to create the true shape of the hole. Usually a circle becomes an ellipse. Why it matters? Without the auxiliary view, a 30-degree hole would appear as a distorted ellipse in the front view, making it hard to read the true diameter. The auxiliary view gives the exact size and location. Analogy: imagine looking at a tilted book on a bookshelf. The front cover looks like a slanted rectangle, but if you take a photo from directly above the auxiliary view, you see the true shape, a perfect rectangle. The same principle applies to engineering drawings. Okay, tips. Keep auxiliary projection lines parallel to the principal projection lines to maintain consistency. Use thin dashed lines for hidden edges in the auxiliary view. Always label the auxiliary view with the angle of inclination for clarity. Problem statement sample. A part has a point A whose coordinates are unknown. The following projected coordinates are given. Drawing uses third angle projection. Front view quadrant 1, 45 mm, 20 mm. Top view quadrant 2, 45 mm, 35 mm. Right view quadrant 3, 20 mm, 35 mm. Determine the three-dimensional coordinates x, y, z of point A. Solution steps. Step 1. Match each view to its component pair. Front view gives x, y x equals 45 mm, y equals 20 mm. Top view gives x, z x equals 45 mm consistent, z equals 35 mm. Right view gives y, zy equals 20 mm consistent, z equals 35 mm consistent. Step 2. Combine the values. X, y, z equals 45 mm, 20 mm, 35 mm. Step 3. Verification. Plug the coordinates back into each projection equation, all match. Variant problem. If one view is missing, use the two available views to solve for the missing coordinate and then check against any geometric constraints. For example, the point lies on a known line or plane. Exam tip: write down the projection equations explicitly before substituting numbers. This avoids mixing up x, y, z with the view axes. Additional exercise. Given the following four-quadrant data for point B in a first-angle system, front -30, 15, top 30, -10, right 15, -10, find x, y, z. Answer: x equals -30 mm, y equals 15 mm, z equals -10 mm. Note the sign changes due to first-angle mirroring of the top view. From this explanation, you just need to break them into segments, and for each segment return phonetic reading style of the segment. The output should be formatted as a JSON instance that conforms to the JSON schema below. Explanation: multiple choice questions on quadrant determination and projection sequence in first angle and third angle systems. 1. In a first angle projection, the top view is placed in which quadrant relative to the front view? Option A, same quadrant as front view. Option B, opposite quadrant mirrored horizontally. Option C, below the front view in the same column. Option D, to the right of the front view. Answer: B. 2. Which of the following statements is true for third angle projection? Option A, the right side view appears on the left side of the drawing. Option B, projection lines are drawn through the object. Option C, all views are placed on the same side of the object as the corresponding projection plane. Option D, the top view is always inverted. Answers. 3. When converting a 3D point x, y, z to its top view coordinates in a first angle drawing, the x coordinate on the sheet is Option A, x. Option B, -x. Option C, z. Option D, -z. Answer: B. 4. In a four-quadrant layout using third angle projection, which quadrant typically contains the auxiliary view? Option A, quadrant I. Option B, quadrant II. Option C, quadrant III. Option D, quadrant IV. Answer: D. 5. If a point appears at -25 mm, 40 mm in the front view of a first angle drawing, what are its y coordinate and z coordinate in the top view, assuming the top view is correctly placed? Option A, y equals 40 mm, z equals -25 mm. Option B, y equals -40 mm, z equals 25 mm. Option C, y equals 40 mm, z equals 25 mm. Option D, unable to determine without additional data. Answer: C. Identify the cutoff line on the front view. Draw a thick line with arrows indicating the cutting direction. Draw the cutting plane as a line at 45 degrees within the front view quadrant. Project the points lying on the cutting plane into the auxiliary plane quadrant 4 by drawing projection lines perpendicular to the front plane. In the auxiliary view, replace the material on the near side of the cutting plane with hatching section lines. and keep the far side hidden. Ensure the auxiliary view follows the first angle rule. It is placed opposite the front view, so the hatching direction matches the convention, lines slanting down right. Front view gives x equals 30 millimeters, y equals 15 millimeters. Top view gives x equals 30 millimeters, z equals negative 20 millimeters, negative because it is below the datum in third angle. Right side view shows y and z, so center equals 15 millimeters, negative 20 millimeters placed in quadrant 3. Check that the auxiliary plane is perpendicular to the inclined feature. Measure the angle between the auxiliary plane line and the feature line. They should be 90 degrees. Confirm that the projected points from the three principal views intersect the auxiliary plane at the same coordinates. Use the transformation equations. Compare the dimensions measured on the auxiliary view with the known true dimensions of the feature, for example, diameter of a hole. Any discrepancy beyond tolerance indicates an error. Point at the origin O000. Projection distance to any principal plane is 0, because the point lies on the intersection of all three planes. In every quadrant, the drawn point coincides with the origin symbol, usually a small circle with crosshairs. Angles: no angle is defined, the projection lines collapse to a point. Point on the x-axis, x equals a y0 z0. Front view xy coordinates a 0 lies on the horizontal x-axis of the front quadrant. Top view xz coordinates a 0 identical to front view, because y0 appears on the x-axis of the top quadrant. Right view yz coordinates 0, 0 projects to the origin because y0 z0. Projection distance to the front plane absolute z0, to the top plane absolute y0, to the right plane absolute x, a perpendicular distance from the point to the yz plane. Angle between the projection line and the plane is 90 degrees perpendicular, but the line itself lies in the plane, so the apparent angle is 0 degrees in the view. Point on the y-axis 0b0. Front view 0b on the vertical y-axis. Top view 0, 0 at origin because x0 z0. Right view b0 on the vertical axis of the right view. Distances to front plane absolute z0 to top plane absolute x0 to right plane absolute yb. Angle: same reasoning as x-axis case. Point on the z-axis 0, 0c. Front view 0, 0 origin. Top view 0c on the vertical z-axis of the top view. Right view 0c on the vertical z-axis of the right view. Distances to front plane absolute c distance, from point to xy plane to top plane absolute 0 to right plane absolute 0. Angles: projection line to the front plane is perpendicular 90 degrees in the front view. The point appears at the origin, so no visible angle. General formula for projection distance. For a point P, X, Y, Z. Distance to front xy plane absolute z. Distance to top xz plane absolute y. Distance to right yz plane absolute x. Angle of the projection line with respect to the drawing plane is given by theta front equals arctan of open parenthesis square root of x squared plus y squared close parenthesis divided by absolute z. Similarly for top and right. When the point lies on an axis, the numerator becomes 0, giving theta 0 degrees, the line lies in the plane. When the point is off axis, the angle indicates how deep the point is relative to the plane. Practical use in CAD: these distances help set up proper view offsets and ensure that hidden lines are drawn with the correct depth cues. Analogy: think of a lamp shining down on a table. The distance from a coin on the table to the lamp is like the z distance to the front plane. The shadow cast on the table, the projection tells you how far the coin is from the light source.